Welcome to a brand new episode in the Science and Technology Unleashed series. My name is Rahul Ramzanli, and I will be your host for this episode. Maulana Haji Muhammad said, from the very beginnings of Islam, the search for knowledge has been central to our cultures. Join us as we explore the applications of chemistry in our lives and on Earth. Our first guest is Dr. Zulika Kurji, Assistant Professor of Chemistry at St. Mary's College of California in the United States. She earned her bachelor's degree in biology and chemistry from Cornell University and a PhD in chemistry from Caltech. Her research interests are in smart materials, which are materials that can be designed to have properties that change in response to something. She has structured her career to include teaching undergrads because introducing people to science is one of her favorite things.
My name is Zulika Kurji. I grew up in Calgary and I did most of my schooling in the United States, and now I live in the California Bay Area, where I'm an assistant professor of chemistry at St. Mary's College of California. My research lab focuses on materials that change shape in response to light. So light is the stimulus and the bend that they make is the response. So here's an example of these paper tweezers that we built where we put our material sort of in the back and we shine light on it. And as the material contracts, the paper tweezers ends come together. So you can see the light hitting our material and the material sort of unfolding. And then as the light gets taken away, it relaxes back to where it was before. So it's a proof of concept to say, here is our material doing work. Here's our material doing something. And to sort of show and have people use your imagination and what other kinds of things that could be done here. The way we do this is by using liquid crystal elastomers. Liquid crystals are molecules that, because of their shape and their chemical properties, they tend to sort of lie next to each other and align in the same direction as their nearest neighbors. You can kind of imagine long grain uncooked rice sitting on a plate. Most of the molecules are going to lie, almost all of the rice is going to lie parallel to the plate. There are not going to be very many rice grains that are like standing up on the plate. And that's kind of a similar thing to the way liquid crystals align. What's special about liquid crystals is that they, when you have a small disruption somewhere of a liquid crystal, it can sort of induce its neighbor to also have a similar disruption. And the next neighbor will do the same thing. They can propagate that signal, that change across the whole bulk of the material. We call this amplification. So a very small change can be amplified throughout the whole liquid crystal, making it easier to see or use. And scientists and engineers harness this property by sort of locking them, liquid crystal molecules, these small molecules, into these big plastics called polymers or elastomers. My lab has adapted a known liquid crystal elastomer system to change shape, to bend in response to light. We do this by chemically adding a molecule called azobenzene. And this really small molecule, when you shine light on it, it bends. And this particular azobenzene that we added will bend in response to blue or green light. We were successful in making a material that, when you shine light just from a laser pointer, something you can buy on Amazon or eBay, blue or green one, we were able to make our material bend. And then when you take the light away, it'll relax back up to its original position, and this process can be repeated reliably many times over. What I'm really interested in is sort of the science behind what's happening at a really small level, the atoms and the molecules, right? What happens engineering-wise if I change the amount of that azobenzene material in there? If I put in more, well, can I bend it more? What happens if I put in less? What's the smallest amount of this I can put in and still make a reliable bend? What if I make my material stiffer? How will that affect the overall change of shape? Some other sort of technical questions are, is it really just the light that's making this big effect? Or is it something like the heat of the laser combined with the light? And how can I design an experiment that can isolate those two facts and come up with a better idea of what's going on? But you don't have to be necessarily focused on the technical things. Sort of, if you're interested in chemical engineering, you might think of the applications. And you can kind of imagine that what we have is something that bends remotely. I don't need to have something right where the bend is. I can trigger it with light from far away. So you can imagine maybe a minimally invasive surgical instrument where I maybe have light going up a fiber optic cable, and you have a little this material at the tip or all across the bulk, and you can weave your material in through some complicated part of the body, and then you don't have to maybe cut someone open. So I really like in chemistry that a small change can have a really big effect. And by knowing what's small, by knowing the chemical bonds, the atomic structure, the way things react and with each other, you can have a really big effect. I think it's just beautiful. I also like that in chemistry we have a lot of tools that you can go in and investigate these sorts of things. I think it's really wonderful to be able to say, well, I want to investigate this. I know what I can do to do that. I might not have access to that equipment. I might have to find someone who can help me, but I can figure out a lot based on the things that are available to me. I also think it's really fun. I think it's really fun to look at things and watch them move, to look at things under the microscope and find out their pretty colors and they're beautiful. And it's really fun to go into the lab every day and try things. So there were some challenges in my path, and I thought it's important to mention them. And one of them was, after my undergrad degree, I knew that I really wanted to teach. I really wanted to teach at a university if I could make that happen. And to do that, you need to get a PhD. But a PhD is all about research. It's all about taking something, focusing in on a small area and where people don't know very much and investigating the unknown. And that naturally has a lot of uncertainty. It's sort of built in and baked into what you're doing, right? Nobody else has the right answer. Nobody else can tell you if you did it right. Nobody else knows. And I found that really difficult, to the point where sometimes it was hard to, if I went and I collected data, I didn't want to look at it. So what if when I looked at it, I would find out I was wrong or I did it all wrong? So part of my journey through graduate school was to figure out how to deal with that kind of internal anxiety and how to learn to embrace the uncertainty of research. And I think it was great that I had the space and time to be able to figure that out for myself. It's not easy. And if anyone out there is feeling like they would rather sort of hide and not look at what they were doing because they don't know if it's right or wrong and they don't want to be proven wrong, right? I want to tell you that I get that. What I eventually learned is the way something goes wrong can tell you a lot. If your experiment worked perfectly and it didn't have the results you were hoping for, something in there is going to tell you what to investigate next. If your experiment went wrong, something in what happened is going to tell you how to fix your experiment, and you can't know until you try. And if you are avoiding that, you can't learn anything. So the nice thing about spending so much time working with both myself and my experiment is that I ended up learning that I can apply these kinds of tricks and tools that made me a good scientist to my regular life. And if there's something that makes me anxious or makes me want to run away, I can kind of think about, well, I've done this before. How did I do it before to make myself succeed? And it's one of the things that I just want people to know. You're not supposed to be an expert at this going in. Your job is to learn. So you're not supposed to come in with the answers. You're supposed to come in with the questions. And if I can do it, you can do it. It's not easy, but it's worth it. I have a couple of role models that helped me to my success. And the first one was my PhD advisor while I was going through my struggles. It's very easy to tell someone who isn't maybe performing entirely at a high level to, say, this is it, it's not going to work out, right? I'm paying your salary, I don't want you to sit here and waste my time. But my PhD advisor sort of saw the whole person and saw what I was capable of and said, let's take some time to figure out how you can succeed. And because of her, I'm where I am today. And I think that's wonderful. And I hope that everybody can stay in a situation where you have a boss or a mentor or an advisor who is supportive enough for you to see you through challenges, because your life is going to be full of challenges, whether or not you're a researcher or something else. If you are in an environment where somebody would rather berate you or dismiss you, I hope you can find a more supportive one. The second set of role models I have are my parents. They've always valued education so highly, and they've always given us the opportunities and given us the belief in ourselves that we could succeed. I think what they did that was really special for me, though, when I was struggling, is that they showed me that even though they're really proud of who I was and how I was doing and that I was getting a PhD and I was, it didn't matter to them if I turned out to not want it or I couldn't make it through, right? When I was having the major struggles, I said, what if I quit? And they showed me through their actions and their words that it didn't matter to them. They would love me exactly the same amount. They would brag about me exactly the same amount if I had a PhD after my name or if I didn't. And that made me much more safe and free to figure out what I really wanted, and what I really wanted was to continue, and I did. So I can't thank my parents enough for being supportive in a way that didn't make me feel the weight of their expectations.
As we learned and heard, in chemistry, a small change can have a really big effect. Our next guest is Dr. Khalid Muhammad Ali, a scientist and assistant professor in the Department of Experimental Therapeutics at the University of Texas MD Anderson Cancer Center in the United States. He received a fellowship to attend Rice University, where he obtained his PhD in biochemistry. His research involves developing new protein therapeutic agents for cancer treatment.
My name is Khalid Muhammad Ali. I'm an assistant professor at the University of Texas MD Anderson Cancer Center in Houston, Texas. I'm a biochemist and a scientist involved in cancer research. There are many branches within chemistry, which is, broadly speaking, the study of elements and compounds, their composition, their structure, how they interact with each other, how they change, if there's a chemical reaction, and so on. One of the branches of chemistry, which is the area that I specialize in, is biochemistry. Biochemistry explores all of the chemical processes that occur in living systems. So the chemistry of biology, if you will. It really is the key discipline in understanding human diseases and how to treat them, such as diabetes, infections, heart disease, and cancer. So as a biochemist and as a cancer researcher, I try to understand what changes have occurred from normal state to the cancer state at the genetic level or at the cellular level to give us clues on how to prevent, treat, and cure cancer. I work in an area of cancer research broadly described as targeted therapy. What is targeted therapy? Well, targeted therapy is a cancer treatment that uses drugs to target specific genes and proteins which are involved in the growth and survival of cancer cells. So when cancer cells begin to successfully ignore the body's instructions and begin to continuously divide and to spread to other parts of the body, what they do in most cases is they change the number and the types of proteins that are on their cell surface from those on normal cells. So their cell surface signature changes. So we look for particular proteins that are expressed at much higher levels on cancer cells than on normal cells. And we use either antibodies or other natural proteins that are known to bind to them, what we call ligands, and combine these antibodies or ligands in a precise way with toxic proteins or chemicals that the cancer cells take up and then die. So this is what we call sort of the Trojan horse approach. So if you recall the ancient Greek story where the Greeks concealed themselves into a large wooden horse to trick the Trojans into letting them in. Nowadays you use this term in computing as well. So this is sort of the type of approach we take with targeted therapy. Another thing that cancer cells do is that they send their own signals to the surrounding environment and to the rest of the body to recruit normal cells, cells that your body needs for normal function, to help the cancer cells now to grow and to spread. So another area of my research is to try to identify what those particular cells are and to block them, again, in a very targeted way from responding to the signals that the cancer is sending. And the third thing we try to do is we try to understand why some types of cancers are sensitive to a particular drug or a therapeutic, and others are resistant to that same drug or therapeutic. So we do this by developing a complete profile of each type of cancer cell that we're interested in, the genes that they express, the proteins that they express, and so on. And then we develop a hypothesis on what aspect of the profile can account for the sensitivity or the resistance. So we then test these hypotheses by turning on or off those specific genes or pathways, and then treating again with those drugs to see if the response has changed. So this allows us to come up with new potential targets for cancer treatment. So all of our research is done as a team, from picking a target to developing it, to producing enough fusion proteins to test first on the cancer cells or the patient samples in the laboratory, then in research animals. So then we partner with others for large-scale manufacturing and testing. So in terms of quality of life or the impact on quality of life, cancer is unfortunately a disease that affects millions of people around the world, not just the patients, but also their caregivers. So for many cancers, the standard of care includes treatments that are poisonous to cancer cells, of course. But unfortunately, it's also toxic to normal cells, which results in severe side effects. So if we can deliver a drug that is delivered only to the cells that you're targeting, then you can actually deliver much higher doses, which can increase the overall survival and disease-free survival with fewer side effects. And that improves the quality of life. So there certainly are a lot of challenges in cancer research. We sort of joke that research really means research. So you have ideas of what may work, but in the end, some work and many of them don't. So some therapeutics will work really well in the laboratory or the cells in a dish, but they won't work once you move to a more complex disease model. So I've had some really promising projects discontinued because of that, or because the focus area of the funding agency changed. Really, you just have to sort of recognize that it's not easy, it's not meant to be easy, but you just take a deep breath, you think about what you've learned and how to improve and how to keep going. Another challenge that comes up frequently is obtaining grant funding, which is something most researchers in an academic setting have to do. So writing or submitting grant applications is really an exercise in resilience and in persistence, because you're always hoping for the best, but you understand that things won't always go your way. The most exciting thing about the future of chemistry and biochemistry is that they're very relevant to address the needs of society, and there's still so much to learn. I only talked about biochemistry in cancer research, but this field is very applicable to areas such as bioremediation of polluted soils, methods to increase the biological capture of carbon, developing new feedstocks, genetic interventions to eliminate human disease using existing technology like CRISPR, or even developing newer, safer drugs to treat disease. These are just some of the areas where chemistry, and particularly biochemistry, are heading in the future. So really, in terms of advice, I would say that if this is a field that you see yourself and you want to explore, I really recommend that you learn as much about it as possible, because there's lots and lots of resources on the web. First of all, talk to people you know, get in touch with people you don't know. Nowadays you can do that so easily. Talk to them about what their work day is like, what they enjoy about their work, and just as importantly, what they don't enjoy. Ask a lot of questions. If you can spend time volunteering at or shadowing someone who works in the area you're exploring, then that'll also help you to understand. But most of all, I think, and this I think really applies in anything you do, is be prepared to work hard. Be prepared to learn, unlearn, and relearn. Be accountable, and also be a collaborative and a team player. I feel like I've been very lucky to have a very diverse background. I was born in Karachi, Pakistan. Both my parents' families are from Gwadar, which was at that time a small fishing town on the west coast of Pakistan. I grew up in Kuwait, where my father had gone to work since he was 16 or so. So I have really great memories of playing soccer every Friday morning with other Jamati members. From 7th grade onwards, I attended an English high school in Kuwait, which had students from all over the world. In fact, one of my biology classes had 10 or 11 students and every one of us was from a different country. After I completed my advanced level or A-level certifications in physics, chemistry, and biology, I spent 1 year at Creighton University in Omaha, Nebraska. And then I graduated from Texas A&M University in College Station with a bachelor's degree in biochemistry. From there, I went to Rice University in Houston, Texas to complete my PhD in biochemistry. So for me, I really feel like the inspiration to do what I'm doing sort of came gradually, but the common thread is curiosity and just sort of wondering how things work. So the possibilities, so much that is unknown, so many opportunities to be creative, to make an impact, to improve and save human lives. That's really what makes me so passionate. You know, as much as we think we know now compared to what we knew 10, 20, 30 years ago, there's still so much more to learn, so much more new technologies that are coming up that help you discover, to apply science for, so many different uses. And that's what makes research so exciting, and that's what makes me so passionate.
That was interesting to learn about cancer cells and how their cell surface signature changes. Starting with Jabir bin Hayyan, a student of Imam Jafar Sadiq, Islamic scientists transformed the study of Greek alchemy that they had inherited. Bin Hayyan established a framework for conducting, recording, and repeating experiments, thereby laying the foundations of modern chemistry. He also invented many of the basic laboratory equipment in use today and outlined key processes like distillation, filtration, crystallization, and others. Our next segment is on Islam and science.
Plastics, perfumes, medications. The chemistry underpinning much of what we take for granted is the result of curious and courageous scientists of the past. The foundation and framework of modern chemistry stems from the work of early scientists of the past, including Muslim scholars. They ensured that knowledge from the Greek, Egyptians, and Indian subcontinent, for example, was preserved and built upon. This knowledge was later translated and filtered through into Europe, where it was eventually adopted by Renaissance scholars. We begin with Jabir ibn Hayyan. Jabir, also known as the father of chemistry and considered one of the greatest experimenters of his time, transformed alchemy into chemistry. Jabir was the first to experiment with distillation and filtration. His groundbreaking work on acids and alkaline, material classification, and his work on the constitution of metals have survived the test of time. A philosopher and chemist, Al-Kindi was another giant in this field. His pioneering work in pharmacology helped explore the impact of drugs on living organisms. By applying mathematics to chemistry, Al-Kindi was able to determine effective drug dosages, laying the foundations of basic medication. Chemists set up pharmacies and dispensaries in a more systematic way and wrote extensively on pharmacology, sharing healing remedies, prescribing doses, and their side effects. Al-Razi, on the other hand, was a pioneering physician and chemist. He was the first to set up a modern laboratory. He introduced new techniques and designed over 20 instruments for distillation. He created a wide variety of new alloys and compounds. Al-Razi was well known for his study of sulfuric and other acids, and for his discovery of ethanol and its uses in medicine. Chemistry owes much to medieval Muslim scientists, including the invention of perfumery, soap bars, kerosene, and antiseptics, all products that are indispensable and in use today. Their inquisitiveness, use of the experimental method, and foresight paved the way for the advancements that were to come in the modern era.
Our next segment covers an exciting weekly rundown of global news on emerging technology, scientific trends, and other extraordinary advancements. Narrated by artificial intelligence, these have been handpicked just for you.
Canvas is a robotics startup that was founded in 2017. The startup's robotic arm has sensors that automate the process of drywall installation. Once Canvas perfects the process, it will move on to automating other construction tasks. The robots are operated by trained workers, and it plans to expand to other cities as the robotic and AI worker market has seen a boom in recent months. Amazon Sidewalk is Amazon's local networking system that extends smart homes into smart neighborhoods. The technology uses various communication protocols to create a mesh network across the neighborhood so that everyone in the area can achieve better connectivity. For example, the network can ensure that a security camera has adequate connectivity even if it is far from the home Wi-Fi router. While the network can be used to access the web, it has very limited bandwidth. There are some security concerns with Sidewalk, including the extra data that it sends to Amazon. Users can disable Sidewalk, but doing so will opt out all their devices from the neighborhood network. Nanobots that can protect your biological system and ensure that you have a good and long life could be working inside you within the next 10 years. DNA robots are already being tested in animals to seek out and destroy cancer cells. Researchers believe that nanobots could soon deliver drugs to humans with a high degree of accuracy, allowing exact dosages where needed and potentially preventing harmful side effects. They could be used to treat and monitor a wide range of medical issues. Plenty is a startup in San Francisco that focuses on vertical farming technology. It uses robots and artificial intelligence in its vertical farms to optimize the farming process, with a focus on eliminating plant stress. There are limited areas in the world that can grow fresh fruits and vegetables economically, and all of that land is used up. Vertical farming can be achieved anywhere in the world as it is indoors and the environment can be controlled, producing better fruits and vegetables while using 95% less water and 99% less land. It could give independence to many areas that have to rely on imports for food. Scientists were able to create and cancel magnetic fields from afar by running an electric current through a special arrangement of wires. With this technology, it is possible to create a magnetic field inside the body that magnetic nanoparticles can be attracted to. Doctors could use the technology to deliver targeted treatment to specific areas of the body. It can also be used to reduce the noise from external magnetic fields. The next step for the researchers is to build a configuration that allows for the creation of 3D magnetic fields from afar.
Thank you again for watching this week. Our exploration continues next week, and we look forward to seeing you for the next episode. Finally, let's hear what Maulana Hazir Imam said.
This is a time that will call for the very best of truly educated minds. Your skills and specialized knowledge, but also your patience and tolerance. Above all, it will call for your understanding. May you bring reason and hope to all whom you touch in your professional and personal lives, and may you find your work deeply rewarding.